Hello and welcome to the give back video for the Remove Forces and Motion exam. If you've sat this test, chances are that you'll either have been taught forces and motion by Mr. Mosedale or Mr. Norman. I'm Mr. Norman and I'm going to be doing the give back video. The first thing to note is that this date is actually wrong. It was sat in 2015, not 2014. So on to the first question. The graph shows how the distances travelled by two cars X and Y varies with time. First question is, what is the total distance travelled by each car? And we can just read this off. Both X and Y end up at the end of the time, which is 60 seconds, ending up 600 metres away from the starting point. So the answer here for 1 mark is 600 metres. At 20 seconds, how much further has car X travelled than car Y? So at 20 seconds here, we can read off that car X has travelled 200 metres, whilst car Y has only travelled 100 metres. That means that the difference between those two, 200 take away 100, gives us 100 metres as the final answer. 1 mark for reading the two values off the graph, and 1 mark for the answer. How do you know from the graph that car X travelled a steady speed? Well, we know that on a distance time graph, the speed is given by the slope of the graph. Now you can see for Y, it's not travelling at a steady speed at all. In fact, the speed is changing throughout the motion, whereas X, it's a constant speed because the slope is constant. So constant slope or constant gradient would have got you the mark there. Which car is travelling at the greatest speed after 30 seconds? So here's 30 seconds on the graph. Reading up, we see that that's the point we're interested in. X is clearly travelling with a slope that looks like that, whereas Y, it's much more steep, it looks like that. So in this case, the right answer is Y for 1 mark, and the answer is that the slope, the gradient, is bigger for the second mark. Okay, on to the next question. The diagram shows the horizontal forces acting on a cyclist while she's accelerating. We know that she's accelerating here because the driving force is bigger than the resistive force. So if the driving force is bigger than the resistive force, that means that the overall force, or the resultant force, and here in this question it calls it the unbalanced force, is still forward. So that means that she's accelerating in this direction. Now we want to know how it changes as she accelerates. So first of all, we note that at first, the driving force is bigger than the resistive force, and this means that she accelerates. As the speed increases, the resistive force, the drag, also increases. And eventually, in the end, the driving force is exactly the same as the resistive force. This means that there's no overall force, so she stops accelerating. And this is, of course, what we call a terminal velocity. She's traveling at a constant velocity, a constant speed, and that means that she's at her terminal velocity here. Some racing cycles have lightweight frames. Why is it good for them to have lightweight frames? The reason for this is that your acceleration is your force over mass, because F equals ma. So that's worth 1 mark. And then because the force is going to be the same, she's not going to get any stronger, so the force is the same, but the mass is smaller. This means if you're dividing something that's the same by something that's smaller, the acceleration is going to be larger. And that means you can get more acceleration for the same force. In question 3, we've got a speed time graph for a lift. Now, the important thing about this question, in the question, it says that the lift is descending. So it's coming down from the top of a lift shaft to the bottom, and it's starting off slowly, getting faster, and then sort of slowing down. So if you imagine that the floor is down here, the situation we've got is that we've got our lift starting at the top, it's getting faster, travelling at the same speed for a while, and then finally slowing down as it gets to the bottom. That's the situation that we've got here, and it's shown on the graph. So between which times is the lift increasing in speed? It's increasing here as the graph's going up because the acceleration is shown by the slope of this line, so 0 to 2 seconds for 1 mark. What is the direction of the resultant force between 8 and 10 seconds? Well, going back to my little sort of animation here, at the beginning, it's speeding up, then it's at a constant speed, and then it slows down. So the 8 to 10 seconds bit happens at the bottom, and the force on the lift here is going to be in the upward direction because that's what's going to cause it to actually slow down to a stop. So upwards is the direction, and the explanation for that, which is worth the second mark, is that it's decelerating in the downwards direction. Which means, of course, it's accelerating upwards, which is why I've got an upwards force. Finally, we're asked to estimate the height of the third floor above the ground floor. So we want to know what is this total distance that's been travelled by the lift. And to do that, the distance travelled is the area under a speed time graph. So in effect, we've got a triangle plus an oblong plus another triangle. So our first triangle up here on the graph is that one. We get the area of the triangle by doing a half times base times height. Base being 2 here, 2 across, and height also being 2. So 2 times 2 is 4, divided by 2 gives us 2 meters. Next, we've got this other triangle at the far end. Again, we've got 2 here between 8 and 10. So a half times base, which is 2, times height, which is also 2. So 2 2s are 4 divided by 2 gives us another 2 meters. And finally, we've got this large rectangle in the middle. And that's base times height. So our base here between 2 and 8, we've got 6. And our height is still 2, going up to 2 there. So we've got 12 meters in the middle. So our total distance travelled, 12 plus both 2's, gives us 16 meters. The marks here for the 3 areas and the final answer. Over the page. We've got an athlete who wants to jump over a horizontal hurdle and is pushing down on the ground. If the athlete is pushing down on the ground, then that means that the ground experiences a force downwards in this direction. The ground is being pushed down. By Newton's third law, that means the ground pushes up on the athlete with an opposite force, so upwards instead of downwards, and that pushes him upwards. So the force that causes the athlete to accelerate upwards must be an upwards force. And it is, in fact, the reaction of the ground pushing upwards on the athlete. So our marks here, upwards, it's reaction force, and it's the ground pushing on the athlete. 3 possible marks, of which you needed to score 2 to get full marks. Now we've got a graph showing how the upwards velocity changes after leaving the ground. If we imagine our athlete on the ground, so here's the ground. At first, we see that they've got a velocity of 4 meters per second. That must be an upwards velocity. So that tells us that the upwards direction is positive, and we'll need that later. As they are moving upwards, they're traveling upwards at 4 meters per second, but very quickly, of course, they decelerate, stop, and then come back down. And they're going to end up coming back downwards at 4 meters per second, which is shown on the graph at -4 because it's a downwards velocity, not upwards. So that's the situation. We want to know, for the first question, what time do they reach their maximum height? That's going to be when they're stopped at the middle of the motion, so when their velocity is 0. And if we read across, that tells us it's 0.4 seconds.